So now that we've reviewed how to convert from polar to rectangular and from rectangular to polar, let's look at how to find the derivative dy dx if I'm given some polar function. So if I'm given a polar function that is where r is equal to some function of theta, since we know that x is equal to r cosine of theta and y is equal to r sine of theta, dy dx can be represented by, just like it was in parametric equations, dy d theta over dx d theta. Now, plugging in what we know for x and plugging in what we know for y, we end up with this formula here for dy dx for polar, and that is that dy dx is equal to r cosine of theta plus dr d theta times the sine of theta divided by negative r sine of theta plus dr d theta cosine of theta. Now, I never use this formula when I'm finding dy dx, just because that's more to memorize and it's not necessary. Basically, if you remember that x is equal to r cosine of theta and that y is equal to r sine of theta, you're going to take your given r and you're going to substitute it in place of the r here with y and then find that derivative, and then you're going to substitute it in place of the r here with x and take that derivative, and then it ends up being this formula here. So what I do is figure out what is y with my given r, what is x with my given r, and then I take that derivative. So I won't be using this formula, I'll just be using the same thing that we did in parametric equations, where dy dx was, there it was dy dt over dx dt, but here since our variable was theta, it's dy dx is dy d theta over dx d theta, and I just need to make sure that I'm getting myself into the right format by plugging in the given r into both of those formulas. Let's look at how to find that derivative in example 5. So example 5 says to find dy dx and then find the slope of the tangent line at the point 7/2 comma pi over 6, given that r is equal to 2 plus 3 sine of theta. So you're given what r is. In order to find dy dx, you first have to figure out what is y and what is x. Now recall, you know that y is equal to r sine of theta and that x is equal to r cosine of theta. So the first thing you need to do before you find the derivative is figure out what is y and what is x with this given r. Let's start with y. So we know that y is going to equal r, which is 2 plus 3 sine of theta times the sine of theta. Now I have to take the derivative of this. Since I have to take the derivative, I'm going to distribute first. If I distribute, I end up with 2 sine of theta plus 3, and I'm going to write this as the sine of theta squared. Therefore, the derivative dy d theta is going to be the derivative of 2 sine of theta, which is 2 cosine of theta, and then here your derivative is going to use the chain rule, so that's going to be 6, and then sine of theta times the derivative of the sine, which is the cosine of theta. Now I need to find x and then find that derivative. Well, what do we know? We know that x is equal to r cosine of theta. So in this case, x is going to equal r. Well, r is given as that 2 plus 3 sine of theta, and that needs to be multiplied by the cosine of theta. Since I have to take the derivative, again, I'm going to distribute. So distributing my cosine here, x is going to be 2 cosine of theta plus 3 sine of theta cosine of theta. Now I need to take the derivative to find dx d theta. Dx d theta is going to equal, well, the derivative of 2 cosine of theta is negative 2 sine of theta. Here I have to be careful. I have to use the product rule. So it's going to be the first, which is 3 sine of theta, times the derivative of the second. The derivative of the cosine is that negative sine, plus the second, which is the cosine of theta, times the derivative of the first, which is 3 cosine of theta. Distributing, I end up with negative 2 sine of theta minus 3 sine squared theta plus 3 cosine squared theta. So now I need to find dy dx because I was asked to find dy dx. Now dy dx, we find it just like we did in parametric. Dy dx is going to equal dy d theta over dx d theta. So you don't need to memorize this formula here as long as you convert your given into what y is and what x is in polar, and then find those derivatives. So in this case, your dy dx is going to equal this 2 cosine of theta plus 6 sine of theta cosine of theta, and then divided by this guy right here, your dx d theta, which is negative 2 sine of theta minus 3 sine squared theta plus 3 cosine squared theta. Again, you don't need to memorize that formula as long as you take your given r, your given function, and then you find out what is y and what is x. After you find what y is, find dy d theta. After you find what x is, find dx d theta. And then, just like parametric equations, dy dx is dy d theta over dx d theta. So we found dy dx just like it asked for. Now it wants us to find the slope of the tangent line at this given point. So I need to evaluate this derivative at this given point. If I'm evaluating the derivative at the given point, so dy dx evaluated at the point 7 over 2 comma pi over 6, remember this is r and this is theta, would equal 2 times the cosine of pi over 6 plus 6 times the sine of pi over 6 times the cosine of pi over 6 minus 2 times the sine of pi over 6 minus 3, and then I'm going to write it as the sine of pi over 6 squared plus 3, and I'm going to write it as the cosine of pi over 6 squared. Let's get all these values. Well, the cosine of pi over 6 is the square root of 3 over 2. So this is 2 times the square root of 3 over 2 plus 6. The sine of pi over 6 is a half. So that's going to be a half. And then again, the cosine of pi over 6 we know is the square root of 3 over 2. Down here, it's going to be negative 2. Sine of pi over 6 we already said was a half. Minus 3. Sine of pi over 6, again, we already said was a half. And that gets squared. And then the cosine of pi over 6 we said was the square root of 3 over 2. And then that gets squared. If I keep going, these 2's cancel, and that's the square root of 3. And then here, 6 times a half times another half is 6 over 4, and that's going to reduce to 3 over 2. So this becomes 3 square roots of 3 over 2. Down here, this is negative 1. A half squared is a fourth times negative 3 is minus 3 over 4. And then root 3 over 2 squared is 3 over 4 times 3 is plus 9 over 4. Cleaning up the numerator, we notice that we have like radicals. The number in front of the first radical is a 1. So we have 1 square roots of 3 plus 3 over 2 square roots of 3. That makes that 5 over 2 square roots of 3. And in the denominator, it's negative 1 minus 3 over 4, which is negative 7 over 4, plus 9 over 4, which ends up being 2 over 4, and that's going to reduce to a half. Well, notice that I have a denominator of divided by 2 for both of these. If I were to multiply this by 2 and this by 2, I'd end up with a slope here is going to equal, because that 2 will cancel and that 2 will cancel, 5 square roots of 3 over 1, and I don't need to write the over 1. The next thing that we're going to look at is horizontal and vertical tangents. Now these definitions that we are about to look at are the exact same kind of definitions that we saw with parametric equations. Horizontal tangents occur where dy d theta equals 0, but dx d theta does not. And vertical tangents occur where dx d theta equals 0 and dy d theta does not. So just like last time, what you want to do is find all the values, and if there's any repeated, in this case theta, back in section 10.3 we said t, but if we ended up with any repeated values, we had to eliminate that value. So let's look at doing this for example 6. It says find all the points. Since it wants points, we know that we need r and theta. So find the points where the function, which is given as r equals 1 plus the sine of theta, has horizontal and vertical tangency. So I need to find the horizontal tangency. Remember, that's going to be where dy d theta equals 0, and vertical tangency, and that's going to be where dx d theta is equal to 0. So start with horizontal. In order to find the horizontal tangency, I need to find dy d theta. But in order to find dy d theta, I first need to find y. Well, remember, y is equal to r times the sine of theta. In this case, your r is 1 plus the sine of theta. Therefore, y here is going to equal 1 plus the sine of theta times the sine of theta. Distributing, I have y is equal to the sine of theta plus, and I'm going to write that as the sine of theta squared. Then dy d theta here is going to be the derivative of the sine is the cosine, and here I'd have plus 2, and then sine of theta, and then the derivative of the inside, which is the cosine of theta. So now I have to figure out where does this equal 0, because I need to figure out where dy d theta is equal to 0. So if I set cosine of theta plus 2 sine of theta cosine of theta equal to 0, well, I notice that both of these terms have a cosine in common. Therefore, I can factor out a cosine of theta. So if I factor out a cosine of theta, I'd be left with 1 plus 2 sine of theta equals 0. Now that I'm factored, I set each one of these factors equal to 0. I have cosine of theta is equal to 0, and 1 plus 2 sine of theta equals 0. Now I need to figure out where does the cosine equal to 0, and typically we just look for angles between 0 and 2 pi. So if we're looking between 0 and 2 pi, where does the cosine equal 0? We know that that happens at the angles of pi over 2 and 3 pi over 2. Here, in order to solve this, I first need to isolate the sine of theta. I need to get that all alone. So I subtract 1, and then I divide by 2. So I know that the sine of theta is equal to negative a half. Then the same thing between 0 and 2 pi. Where does the sine equal negative a half? Well, that happens at the angles of 7 pi over 6 and 11 pi over 6. So before I actually find the points, what I need to do is figure out where I have vertical tangency to ensure that none of the theta values are repeated, and then I'll find the points. So let's go ahead and figure out what x is, and then where dx d theta is equal to 0. Well, x, remember, is r times the cosine of theta. So in this case, and r is this 1 plus the sine of theta, so I'd write 1 plus the sine of theta times the cosine of theta. Distributing, I end up with cosine of theta plus sine of theta cosine of theta. Now I need to find the derivative. So dx d theta is going to equal the derivative of the cosine, which is negative sine of theta. And here I have a product, so I have to use the product rule. That would be the first times the derivative of the second plus the second times the derivative of the first. The x d theta, if I clean that up, is equal to negative sine of theta minus sine squared theta plus cosine squared theta. Now I have to figure out where does that equal 0, because I need to find the places where I have vertical tangency. Well, if I set that equal to 0, I notice that unlike the blue, I do not have the same term for all three of these. Since I don't have the same term for all three, I can't factor anything out of them. I'm going to have to convert to the same trig function. Since I have more than one sine, I'm going to try to convert cosine squared theta into sines. And I know that I can do that. There's a Pythagorean identity for that. Therefore, this is really negative sine of theta minus sine squared theta, and then cosine squared theta, I know it's just 1 minus sine squared theta. Moving over here to the right-hand side, because we ran out of space. Again, we have negative sine of theta minus sine squared theta plus 1 minus sine squared theta equals 0. So I can combine like terms. That's negative 2 sine squared theta minus the sine of theta plus 1 equals 0. Now I'm quadratic and I can factor it. Typically we don't like the first term to be negative, so I'm going to divide through by a negative to eliminate that. If I divide everything by a negative, I get 2 sine squared of theta plus the sine of theta minus 1 equals 0. Now let's factor the trig equation. So I open my empty set of parentheses. The only things that are going to multiply to 2 sine squared are going to be 2 sine of theta and sine of theta. The only thing that's going to multiply to 1 are 1 and 1. I just need to figure out where my signs go. Well, I need a positive sine of theta in the middle, so this guy has to be positive and that guy has to be negative. So 2 sine squared theta plus sine theta minus 1 factors as 2 sine theta minus 1 times sine theta plus 1. Now that I'm factored, I get to set each one of these factors individually equal to 0, and I get to solve them both for theta. Here, I need to isolate sine, so I need to add 1 and divide by 2. Therefore, I know that the sine of theta is going to equal a half. Then, same interval between 0 and 2 pi, where does the sine equal a half? Well, at the values of pi over 6 and 5 pi over 6. Here again, I need to isolate sine of theta before I solve, so I subtract 1 and I get that the sine of theta is equal to negative 1. Same interval between 0 and 2 pi. Where does the sine of theta equal negative 1? Well, at the angle of 3 pi over 2. So I ended up with all of these answers. For horizontal tangency, it's pi over 2, 3 pi over 2, 7 pi over 6, and 11 pi over 6. For vertical tangency, it's pi over 6, 5 pi over 6, and 3 pi over 2. So the first thing I need to do is determine if I have any repeated thetas. Do I have anything that's alike between the blue, which is my horizontal tangency, and the green, which is my vertical tangency? The answer to that is yes, the angle of pi over 3. So I have to eliminate that value of theta. It's not going to be a place where I have either vertical or horizontal tangency. Now that I've eliminated, I can finally finish this problem off. Remember, it's wanting points, which means I need r and theta. I have all my thetas, I don't have my r. How do I find r? You plug it back into the original function. So let's find out what r is for all of these. So when theta is equal to pi over 2, I know that r would equal 1 plus the sine of pi over 2, and that's just going to be 2. When theta equals 7 pi over 6, r would equal 1 plus the sine of 7 pi over 6, which is a half. When theta equals 11 pi over 6, r is going to equal 1 plus the sine of 11 pi over 6, which is also 1 half. 2 more to go. When theta is equal to pi over 6, I get r equals 1 plus the sine of pi over 6, and that's going to be 3 halves. Last one is 5 pi over 6. When theta is equal to 5 pi over 6, r is going to equal 1 plus the sine of 5 pi over 6, which is 3 halves. Therefore, we have points of horizontal and points of vertical tangency. Let's start with the horizontal tangency. So for the horizontal tangency, our points here are going to be 2 comma pi over 2, 1 half comma 7 pi over 6, and a half comma 11 pi over 6. For vertical tangency, my points are 3 halves comma pi over 6, and 3 halves comma 5 pi over 6. So again, you're looking for points, so you needed r and theta, but we first find all our thetas. If you have any repeated thetas like we did here, you eliminate them. Finally, you find all your r's, and then you list out your points of horizontal tangency and your points of vertical tangency.